Good evening.
Good evening.
Evangelos.
Nice to see you.
Nice to see you as well.
I think that you can now see my screen, right?
Yeah, we see it. Yes.
Okay. Just give me 1 minute. Okay. Hello, everyone. This is Evangelos from Athens. It is a pleasure being here with you tonight. At least for me, it's night. It's been a pleasure working with Professor Makridakis, both in the M4 and in the M5 competition. In the M4, I was a PhD student and I was doing my best to help him organize the competition. It's really an honor to be able to organize with his help the competitions, and I'm sure that Professor Makridakis will do an excellent job with the M6 as well, and I'm very excited to be part of the team. So today I'm gonna try to summarize some things about the M5 winning methods for the uncertainty track. As you all know, there were two tracks, one for the accuracy and one for the uncertainty. I think that the uncertainty track was very interesting because of the difficulties present. I mean, people are more familiar in producing point forecasts and not accounting, let's say, for the risks, but estimating uncertainty is also very useful. And I think that Bob and Anil both gave us a good picture about that. The problem was about forecasting daily unit sales. Okay, for Walmart, there were a total of 42,000, more than 42,000 series to predict. The majority of the series refer to what is called the SKU level, so the product store level of the company. And it referred to over 3,000 products divided in 3 categories in several departments. This is one of the elements that make a difference in the M5 compared to the previous M competitions, the fact that the data were highly correlated in nature, being part of the same category or department. So it allowed the participants to effectively apply machine learning methods and methods that examine what we call cross-learning, so learning from multiple time series simultaneously. And another interesting thing here was the utilization of exogenous and explanatory variables that also was an innovation for the M5 competition compared to the previous M competitions. Now, as Anil and Bob told you, there were 9 different quantiles to compute. Okay, so this is how the hierarchy looked like. Okay, you had to produce forecasts for all these hierarchical time series, 9 quantiles and 28 days ahead. So this gives us, as you can see, about more than 10 million forecasts, and this is exactly why this competition was so much difficult, and even more difficult compared to probably to the accuracy track. Now I won't tell a lot of things about the evaluation because Neil covered that. I just wanted to say that in the original setup of the competition, we used a weighted scheme for scaling the pinball loss. So we we basically assume that more emphasis should be given on more expensive products and products that are fast-moving, in a sense that they contribute more to the company in terms of in monetary terms. Okay, so all aggregation levels were equal for the evaluation. All quantiles were assumed to be equal, again because the M5 competition was more generic and wasn't focused on a particular, let's say, decision-making problem. But each series had a different weight based on the dollar says each series reported. Now, this is an overview of the participation in the M5. In the plot on the left, you can see the submissions made during the competition. The red vertical line indicates the end of the validation phase of the competition, where the participants stopped receiving feedback in terms of performance. And as you can see, there's a lot of participation there, and lots of teams that try to recalibrate their models in the last few days of the competition and submit. Now, what is more interesting is the plot on the right. As you can see here, it's the weighted pinball loss for the participants of the M5. You can see how the scores are distributed and their comparison with the top performing benchmark of the competition, a statistical method, the ARIMA, and a very simple also statistical benchmark, the seasonal naive method. It is very interesting that many teams found it difficult to outperform these benchmarks, but those that did, like the top 50 performing teams, did that by a large margin that on average was higher than 12.5%, and for the winners higher than 20%. So this is just a comment to highlight that we may discuss about how well the winners did, but it is also important for the practice of forecasting to understand that there were a lot of people familiar with machine learning methods that found it hard to beat some of the benchmarks, and this is important for forecasting practice. Now, this is a summary of the top 20 performing methods. I'm gonna stick with the top performing methods because these are the ones for which we have enough information to discuss their performance. And it's also safer, let's say, to discuss what worked best instead of assuming what didn't work best for the rest. So here, with the bold, you can see the team that did best for each hierarchical level. An interesting finding here, and this was also true for the Accuracy competition, was that there wasn't a single method that did best across all hierarchical levels. Okay, so this indicates that horses for courses may be very relevant for hierarchical forecasting as well, meaning that it may be a good idea to use different forecasting approaches depending on the granularity of the data being forecast. Here you can see a summary of the performance of these top 50 performing teams. It's basically the distribution of the weighted pinball losses for each aggregation level. The red dot is the top performing benchmark, the green dot is the winning team. And here you can see that the winning team did an excellent job in all levels, especially the most granular levels. But as you can see, it was not the top performing one across all levels. Okay, so this goes back to my previous slide. Another interesting finding here is that although you can see that all methods did better than the benchmark for the mid and the top levels, there are a lot of difficulties here at the lowest granularity levels, which means that although they on average did better than the benchmark, the differences weren't that large. So this highlights the importance of doing additional research for SKU level sales forecasting. This is the same table as before, again for the top 20 of the teams, and this basically repeats the story of the previous slides. As you can see, again, the winner did best in 3 out of 9 quartiles, but it's not the top performing benchmark method across all quantiles. So again, it seems that different methods may be more appropriate for forecasting different quantiles. Okay, so the question here is, how do you make these kind of selections, or how you can combine different methods to optimize your results, etc. And this is, I believe, more important when you try to focus on particular quantiles that may be more relevant for the decisions you have to support. Now, if we create the same box plots as before, but this time for the quantiles, you can clearly see what Anil talked to you about earlier. You can see that there are a lot of improvements over the benchmark for the mid part of the distribution, and it seems that the methods are find it more difficult to outperform the benchmarks for the tails of the distribution. Okay, so again, this is an indication that in extreme cases where, for example, you have to predict the tails of the distribution, and and you have to focus on very granular data, then it may be difficult even with very state-of-the-art performing methods to make a big difference. Okay, there are improvements, but they're not always significant. Now, let's move to the winning methods, which is, I believe, also very interesting to discuss today. I'm gonna start with, of course, with the winner of the competition, who introduced an interesting approach for probabilistic forecasting. What I found interesting with that method was that although the elements of that method, let's say the core algorithms used during this forecasting process were not completely new, the authors found an excellent way to exploit some best practices in forecasting and maximize the benefits that you can get out of this kind of algorithms. In fact, they introduced some innovative approaches to do that. So the winning team based their forecast on light GBM. Okay, the workhorse of the M5 competition. Most teams did use this tree-based forecasting model for producing their forecast, and the winners try to forecast the quantiles directly, meaning that each model had a very particular job, being to forecast a particular quantile for a particular aggregation level. Okay, so that resulted in total in more than 125 models. Okay, very specialized models that were very carefully fine-tuned using cross-validation techniques. I think that cross-validation was what really made a difference here. And cross-validation was used for two different purposes. The first one was to very carefully craft and select features that help the model make accurate predictions. The second one was to fine-tune the hyperparameters of the models. So these validation techniques, let's say in brief, manage to improve the generalization ability of the model. Okay, so be able not to overfit and provide very accurate forecast on the post sample. Now, another very important element of that method was data augmentation. Okay, so this is something we will also discuss in the following slides, and it refers to techniques that you can basically use to increase the sample of your model, remove the element of randomness, and again boost the generalization of your model. Now, in terms of cross-validation, when forecasters, and especially for time series forecasting, try to perform a cross-validation, they basically use what we call the standard time series split or rolling origin evaluation, if you want, which looks like the plot on the right. Okay, so you start with the train set, you test on the following window. Again, you add some data and test to the following window. And this is done because in time series forecasting, and since there is a dependency between the observations, a time dependency, we do not want to leak future information in the past while training the model. Okay, so this scheme ensures that we do not have any leakages. Now, there are some problems here. First of all, the earliest faults are completely unrepresented in any performance measurements, and they receive also higher weights in training. Also, a lot of data goes unused or underweighted. So these schemes sounds like a good idea, but especially when you have a task like the M5, it's not probably the best way to go. Now, what the winners did in order to overcome these limitations was to use what is called a paired k-fold validation. So basically, this looks like the previous validation, but what you do is that you basically remove, as you can see here, some observations in between the train sets and the test sets, and that makes sure that although you are using data that refer to the future, okay, since you do not have information about what is the observations that are very close to that train set, okay, this reduces the possibility of leaking data about the future in the past while training. Okay, so this is an effective way to use future data for validation and still not have the problem of leakage. Now, the winners also use what is called a nested cross validation. Okay, so it's basically a validation within a validation. This helps further boost the performance of the methods. And I think that this was a key element of their methods, making sure through this kind of validations that their parameters and the futures used were very representative. The second and similarly important element was the data augmentation. Although there were a lot of data in the M5 and naturally you could effectively train a model like GBM, There was also a lot of noise in the data because we were talking about count data, where based on and for low granularity data, and as a result, the historical data are highly influenced by randomness. Okay, so what we can do here in order to remove this element of randomness is to try to use your data to populate new series artificially. This can be done, actually in the M5 was done by the winners in a very simple way. They just added some random noise around the original series, like you can see here. So starting from that series, you could basically generate unlimited number of series that follow the same distribution, and still there was some useful information for your model to learn. So this is a nice innovation of the winners. Now let's move to the goods forecasting. Nikolai Mamonov, the runner-up of the competition, the uncertainty competition. Again, we can see that the team focused on light GBM models. However, in contrast to the winning methods, they did not directly predict the time series and the quantiles the competition requested. Instead, they started by creating, let's say, a baseline forecast using a histogram technique, where you draw some probabilities using some variables that account for what the authors call global seasonality, basically, some seasonal effects throughout the year, and also from some local seasonality, okay, weekly seasonality, what happens every week. This was very strong for the M5 competition, with Fridays, Saturdays, and Sundays contributing the most in the sales of Walmart. And there was also another element, a forgetting component, that help the authors produce the probabilities by paying more attention to the most recent observations. So after getting those forecasts from the histogram technique, they started producing some point forecasts at SKU level, using some explanatory variables to do so, and of course light GBM models. The whole purpose of doing that was that although the authors understood that the distribution computed seemed right, the center wasn't well calibrated. Okay, so they wanted, let's say, to approximate a new median for the distribution in order to move slightly to the left or to the right the distribution they have computed in the previous step, and using this trick get a better result. Now the process here was quite complex, because there was also a model that performed a top-down aggregation and a bottom-up aggregation. So we basically had a hierarchical forecasting exercise. This is a summary of what the winning team did. Okay, you can see that we start with the estimation of the distribution. We have some forecasts from light GBM models that help us calibrate our results to get the final estimate. And here is, you can see the improvements reported over the original histogram algorithm. Okay, so we can see that especially close to the test set of the competition, the improvements are significant. This is the third winner of the competition, Konstantinos Voglis and Ioannis Nasios. They also used light GBM models, but this time we see for the first time the utilization of neural networks as well. These neural networks were feed-forward ones. In total, we have 27 models that are combined. The majority of the models are neural networks with multiple variations, and 11 of those are light GBM models.
5 minutes left.
Thank you, Maria.
Thank you.
And the trick here was to basically introduce some multipliers after estimating through these models the medians, in order through these multipliers to indirectly specify what the distribution would look like. Okay, for most of the levels, these multipliers were symmetric, for the lowest were asymmetric. And this is what this result you can see here. As you can see, the multipliers are very large, okay, for the tails of the distribution, for the SKU levels. Here, the multipliers are smaller, and more symmetric. And here you can see the improvements by adding the light GBM, the Keras neural networks, okay, and by doing some adjustments how you can improve the rank of the method. The fourth winner, here we have two neural networks, LSTM neural networks. We can see here again that the winner used some augmentation techniques and strong cross-validation strategies to get some improvements. And again, we have direct predictions for getting the probabilities. And the other two winners, the fifth and seventh position, use another technique. They do not recalibrate the median. They do not directly predict the probabilities. Instead, they get some point forecast. Based on that, they estimate the residuals of the forecast, and then they use these residuals either to empirically estimate the quantiles or to estimate the quantiles by assuming a theoretical distribution like the normal one. Okay, so basically you can see three different approaches for solving the same problem by the top 7 teams of the competition. Here is a summary of the results. Okay, of course, we can clearly see that we should be exploiting state-of-the-art machine learning methods. Either this is a light GBM model or a neural network. Let the models learn across multiple series, account for nonlinearities, and capture complex data relationships. The element of combinations, again, very important. And here are some new findings, because the previous one were also true for the M4. Invest time on accurately calibrating your forecasts. This was mostly done by creating more accurate predictions for the median and using that median for estimating the rest of the distribution. We can also see that all the winners used very detailed, proper cross-validation strategies. Okay, so this is a message for the rest. Augment data, also a new element from the winning teams. Use explanatory variables. Okay, I think that these basically summarize what the winners did.
Thank you very much, Evangelos. Thank you. We have time for just one quick question. Take the first one in the Q&A section, please.
Q&A, let me see. How stable do you expect the results are if we scored against the next 20? There's a comment from Matt. How stable the results are when we evaluate the forecast for different days. I think that there were some minor variations from week to week, but since the forecasting horizon was quite long, in absolute terms, the weighted pinball loss did not change that much. Okay, in a competition where the accuracy even in the fifth digit may cost you 3 or 4 positions. It's very competitive. It may, make a difference. But in practice, I can tell that the results were quite consistent, and this is also evident. If we compare the results between the validation and the evaluation period. However, it would definitely be better if we had considered, let's say, a rolling origin evaluation to account for seasonal effects, for the complete period.
Thank you. Thank you very much. Good night, Evangelos. And
Good
let's
night.
move
Thank you,
on.
Maria.
Bye.